I'm going to solve some sample problems on simple harmonic oscillations. So this is the first problem. So here you're given this graph of simple harmonic oscillation. This is the oscillation. It's a position versus time of an oscillating mass. It's given a complete cycle, and it's asking the following questions. First question is what's the amplitude, which is really easy. So just by looking, so how do you calculate the amplitude? Amplitude is just the maximum vibration, right? Which is this, measure from the mean position, measure from this axis, or this, right? So amplitude is just 10 centimeter, right? 0.1 meter. That's it. So second is what is the time period and frequency? Remember, period is actually the time for one complete oscillation. So here this is given one complete full oscillation, right? From here to here. So that should be, so scale is 5, 10, 15, 16 seconds. So time period, which is big T, is 16 seconds, right? Or you can do trough to peak, right? And then twice of this, right? And if you are given many waves peak to peak, you can just do peak to peak. Or so in general, it's time for one oscillation. And frequency is just the inverse of T, right? So 1/16, but time period must be in seconds when you calculate the. So 62.5 -3. So this is 62.5 milliseconds. Millihertz actually. Okay. So that's the frequency. Just 1/. This hertz is the. This is wrong actually. It should be hertz. Is the unit for frequency. So see, what's the angular frequency? Remember, angular frequency is just comparing with the rotational motion. Is just 2 pi f. Okay. So if you do that, so 2 pi and f, right, is 0.39, and the unit of angular frequency is radians per second. So next is what's the initial phase, right? Initial phase, because it didn't start from 0 or from the maximum peak. So it has some initial phase, initial state, right? So how do you find? So you go with this position function in simple harmonic motion. So we use cos function, right? Omega t plus phi. So you just need to find what's the x displacement. What's the displacement x at t0 second? You have to check the displacement at 0 seconds. So what's the displacement at t0? From here at t0 0 seconds, the displacement is so 1 2 3 4 5. So its square is 2 centimeter. So 4 centimeter. Okay. Is the displacement at 0 seconds. So then you put it here. So x at t0, right, is 4 centimeters. So just keep everything in centimeter. 4 centimeter. Amplitude doesn't change. Amplitude is 10, right? Cos. So omega t, we make it because that's the reason actually we found x as t0. So if you put t0 here, this becomes 0 plus phi. So your phi, which is the initial phase or phase difference, right? Phase angle is inverse cos 4/10. That's it. So if you do that, 66.4 degree. Okay, you can just keep it in degrees. So that's how you find the phase shift or phase angle, initial phase. It's called initial phase. So finally, right now, summarizing everything up, it says write the mathematical equation for this given oscillation. So then you just write this equation down because we already know everything, right? So this is our simple harmonic oscillation for position, and we already know all the values. 10 centimeter. Cos omega we have already known 0.39, right, radians per second times t, plus phi is 66.4 degree. So that's going to be your complete equation for that describe this oscillation. Okay, and you may want to convert back to radians if you want, or just mention degrees. So here's the next problem, which is also pretty similar to the first one actually. So you're given the equation, simple harmonic equation in terms of position function for an oscillating mass. So the mass of that oscillating mass is 50 grams. So this could be a simple pendulum, this could be a mass and spring oscillator, and you're given this equation. So what's the equation? The position function 2.0, amplitude is this, right, centimeter, cos 10, it says this is radians per time t plus pi over 4. Okay, so based on that, now it's asking various questions. So what's the amplitude? So it's really easy. So this has to be the amplitude, right? So just compare with the standard equation, a cos omega t plus phi. Okay, that's it. So amplitude must be 2 centimeter. That's the first answer. That's really. What's the period? So period is, again, you have to compare omega, right? Omega must be 10 here, right? If you just compare with the standard simple harmonic oscillator equation, omega must be 10. So and omega, what's the relationship between time period and period? T is 2 pi over omega. So 2 pi over 10 is 0.63 seconds. That's the period of this oscillation. What's the spring constant? So this is a mass and spring oscillator. So again, if you remember, omega square is k over m, one of the formula for mass and spring oscillator. Mass, spring, right? Oscillator has this relation, and then it's asking what's the spring constant. No, there's just okay. Omega is square root of k over m. So omega square is k over m. So spring constant k is m omega square. So mass of the oscillator is 50 gram. So 0.05 in kilo. You must convert into kilograms because we are doing everything into standard units. And omega square is omega. We already know omega, which is 10, and square. So that's the spring constant, which is 5 newtons per meter is the unit. That should be the spring constant of this spring. So D, what's the maximum speed, right? Remember this. So this is a friction. It's oscillating on a frictionless surface, right? It's oscillating to and fro on a frictionless table. So if you remember from the theory, the oscillating mass will have maximum speed at x0 position. Or how do you find that? So if you know the formula, you can directly use that, but if you don't know, you have to do this just one step. So going back to the position function, this is our position of oscillating mass change, right? So just to find the speed, you just take the time derivative of this, right? And this is going to give you negative a coefficient omega sine omega t plus phi, right? So your velocity function came out a omega and some sine function, right? So this is something like that. This is negative v, you can say v naught sine omega t plus phi, right? So that's how velocity function changes for an oscillating mass. So this is the maximum velocity. This is called velocity amplitude. This you can call velocity amplitude, which is nothing, is just if you plot the velocity, right, versus time, this is the velocity amplitude, v naught, which is this. So velocity amplitude, which is the maximum velocity, right, is simply a omega, its magnitude. That's it. And we already know a, which is 2 centimeters, 0.02, and omega is 10, right? It's 0.2 meters per second. That's the maximum speed. Okay, that's it. And a couple more things. Next part is, let me do it here. What's the total energy? So total energy for a mass and spring system, total mechanical energy is if you remember the formula, it's also on the formula sheet. Just 1/2 kx square. 1/2 k is the spring constant, which we have already calculated. Amplitude is just 2 centimeters, 0.02 square. So that's the total energy, mechanical energy of the oscillating 0.001 joules. Right? Just 1 millijoules. Okay, now next, what's the velocity at 0.4 seconds? Remember, the velocity is oscillating, right, over time. So it's asking what's the velocity at this particular time, 0.4 seconds. So then after taking the derivative of this, you're going to get this velocity function, right? You just use this. That's it. So velocity function, let me write down the velocity function. Negative a omega sine omega t plus phi. Okay. And that's it. So and you're calculating velocity at time is 0.4 seconds. So velocity at time is 0.4 second is negative, so a is 0.2 centimeter, which is 0.02. Omega is 10, and sine omega is again 10. Time is 0.4, right? I'm multiplying this plus phi is pi over 4. That's the initial phase. Keep in pi over 4. So that's your answer. So velocity at 0.4 seconds, right, is that much. So but make sure this, your calculator must be in radians when you calculate that, because these are in radians, right? 10 is in radians, pi over 4 is in radians. Your calculator, make sure, this is where a lot of people get confused. Calculator must be convert calculator into radians, and if you do that, it's going to be negative 0.2 meters per second is the answer. That's the velocity at 0.4 seconds. So here's the next question. So a classic wooden toy hangs from a spring and lets it oscillates up and down. If the toy is raised up 10 centimeter before you release it, and then if you release it, it makes 4 complete oscillations in 10 seconds. Right? And these are the questions. So here's the question actually. So you oscillate it by first, just by, you know. So I'm just gonna write down the symbol for that. This is the toy, right? You raise it from your x0 position is right here. This is the equilibrium position, right? You raise it by, before you release oscillate, you raise it by it says 10 centimeter. So that's gonna be your amplitude, right? That's going to be your amplitude, and then this will just follow a symmetrical oscillation like that. This will go below 10 centimeter and above 10 centimeter. So it will oscillate above this equilibrium position. That's how it oscillates. So amplitude is 10 centimeter, okay, 0.1 meter, right? And it says it makes 4 complete oscillations in 10 seconds. So from this information you can find the time period. So how do you find the time period? So time period, which is big T, right, is we're solving A, is total time divided by total oscillations, because time period is just the time for one oscillation, right, by definition. So total time is 10 seconds by 4, so your period is 2.5 seconds, and it's actually also the so frequency is just inverse of reciprocal of period, and that's gonna be your frequency. So frequency is now, right, you can calculate the frequency from here. So 0.4 hertz is your frequency. Okay, that's the first part. Second part, what's the toy's maximum speed? So we have already done in somewhere, right? So maximum speed is v naught, just the velocity, amplitude. The magnitude is just a omega. So amplitude is 10 centimeter, which is 0.1, and omega is, omega is 2 pi f, right? And because we already know f, so 0.1, 2 pi, 0.4. So that's your maximum velocity during this oscillation. Okay, and maximum velocity, if you do this calculation, 0.25 meters per second. Okay, next, which is the last part, is what are the position and velocity at 4 seconds after you release the toy. So at t, so because it's position and velocities, everything is changing here. This is position versus time, and if you do the velocity, it will be a sine function. So they will have phase difference between this. So everything is changing, right, over time. So it's acting at 4 seconds after you release, right? What would be the position? What would be the velocity? And just use the position and velocity function. So position function is a cos omega t plus phi, but phi is 0, right? Because you release from maximum amplitude. You release from 10 centimeter, right? So amplitude, your phase angle should be 0 because you start from maximum position, right? You start from your amplitude. So if you calculate this initial phase just by putting x as a, then phi will be 0. So that's your xt is 4 second. Amplitude we already know 0.1 meter. Cos omega is 2 pi, 0.4 times time is actually at 4 seconds, right? That's it. So negative 8.1. So if you convert back, so at 4 seconds, this is the position. So it could be, position could be positive or negative. It just turn out negative. And similarly, velocity function is given by negative a omega, now sine, right? Because the derivative of cos is sine, negative sine omega plus phi. Just do the same thing. Negative, this is 0.1, omega is 2 pi, frequency is 0.4, and sine omega is again 2 pi, 0.4, and time is 4 seconds, and plus phi is 0, right? Because here's the initial phase shift is 0. Okay, but again your calculator must be in radians. When you do calculation, and your velocity function, right, at t is 4 seconds. Your velocity at 4 seconds is a positive 14.7 centimeters. So I have converted to centimeter per second. That should be your answer when you do calculate. Okay, so that's how you can find now position and velocity at any time, right, if you want. So just by using the functions. So here's the next problem. It says a 300-gram oscillator has a speed of this when its displacement is this, right, and this speed when its displacement is this. What is the oscillator's maximum speed, right? So it's just this problem is so I forgot to mention, is also for a mass and spring oscillator. So this is oscillating, right, horizontally like this, and it's acting. It gave you the mass of this oscillator is 300 gram, 0.3 kilogram, and it gave you two different values. So it's acting. It's given at displacement, initial displacement 3 centimeter. What's the velocity? The velocity was 95.4 centimeter per second. And when its displacement, when its position was 6 centimeter, these are all given, okay. Its velocity is 71.4 centimeter per second. You can convert everything into standard unit. So these are the given, okay, because position and velocity is both changing, right? So based on that, what's this action? What's the maximum velocity? That means when this reaches here, right, at the equilibrium position, what's the velocity? Velocity will be maximum at x is 0, equilibrium position. So that's why. So then you can just use the energy conservation to solve this problem very easily. Okay, first we need omega, right? Because we need V max is a omega. The magnitude of the V max, right, is a omega. You need amplitude and you need omega, right? So let's figure out first, let's see what we can find from energy conservation, right? You can see U plus K initial is U plus K final, and U is, so here there's no gravitational potential energy because it's oscillating in horizontal surface, frictionless horizontal surface. There's no friction as well. So U is the spring energy, 1/2 K initial position square, plus kinetic energy is 1/2 m v1 square, right? Same thing, the spring final 1/2 K second position square plus 1/2 mass v2 square, right? That's the energy conservation equation. And then half, so half will cancel out as a common factor, and K, so these are x1 v1 x2 v2 are given, so I'm just solving in standard unit. v1 is right, no, there is a mass K, you can't common factor, there is a mass. Okay, right hand side is K x2, which is 0.06 plus m, mass is given 0.3, okay, and v2 is 0.71. I'm converting everything into standard unit, right? So okay, so put the mass as 300 grams, 0.3 kilograms. And then now you have only one variable left. You can solve for K by playing with this equation. You can solve for, so K, if you solve that, K will be this 44.5 newtons per meter. Okay, why you gonna need K? Because you need omega, right? So then once you find K from here, this energy conservation, omega will be just K over m, remember, right? So 44.5 divided by mass of the oscillator is 300 gram, 0.3. So omega is 12.2. So its angular frequency is this, right? So we got omega. Now you need one more thing, amplitude of oscillation. So how do you find that? So amplitude you can find with one of the total energies. Now you can, since total energy doesn't change, right? Which is constant if there is no friction. This is the formula for total energy in a mass and spring oscillator. So since we already know K, and we can find amplitude, right? Because the total energy you can use one of these, right? K1 or K2. So 1/2 K x1 square plus 1/2 m v1 square, or you can use 1/2 K x2 square plus 1/2 m v2 square. So one of those, because total energy remains constant. So again, half will cancel out. So K is known. So mass is given, velocity is given, x1 is given, right? K we have found. So then you can solve for amplitude. So it turns out 0.084 meters. So once you have A and omega, you can find the maximum velocity, the velocity amplitude. It's just A omega. So A is 0.084 and omega is 12.2. So V max in this oscillation turns out 1.02 meters per second, just about 1 meters per second. Okay, so it's a little tricky. So here's the next question. This is on simple pendulum. There are two parts. The acceleration due to gravity on moon is 1.62 meters per second square. What is the length of a pendulum, right, whose period on the moon matches the period of a 2-meter long pendulum on Earth, right? So first you have to find out what's the time period on Earth whose length is 2 meters. Okay, so period is for a simple pendulum is, remember, on Earth, right? It says on Earth you use 2-meter long pendulum. So first find that out. So this is 2.84 seconds. So it's now asking what would be the length if you do the same experiment on moon, whose gravity is 1.62, what is the length of the pendulum you need if you do the same thing on moon, actually having the same time period, right? So T, now do the same thing. We are finding what's the length on moon needed to have the same time period. This is same based on the question. And on moon, actually don't use 9.8. Moon is acceleration, gravity is this. So T moon is, it says mass with same time period, right? To have the same time period, what's the length of the pendulum you need actually on moon? So it's 2.84 2 pi. So we are finding length of the pendulum required on moon. So and just solve this for L. So 0.33. You just need much shorter length to have the same time period. Okay, second part. The period of a shortened pendulum on Earth is 1.2 seconds. What would be its period if the length is doubled? Okay, and this is, you can solve in many different ways. The shortest, actually the easiest one is you just solve two equations, set up two equations. And so T1 is, right, 2 pi L1 over G, right? When its length is L, right? So T2 now, when length is doubled, let's call T L2, right? Where L2 is twice L, 2 times L1, which is 2L, right? So then, so it's gonna be these two equations, right? 2 pi twice L over G, right? And let's call this equation number 1, 2. And we're finding T2, right? T1 is given. T1 is 1.2 seconds. So T2, just take this ratio since we're solving T2. So if you divide this by that equation, so everything will cancel out, right? 2 pi twice L over G, 2 pi L over G, right? So everything will cancel out, and then it will be just square root of 2. So T2 is just square root of 2 times T1. That's it, square root of T, and T1 is 1.2 seconds. So time period will be increased like this. Time period will not increase linearly because it's a square root relations. So if you double the length, its time period will be 1.7 seconds as opposed to initially 1.2 seconds. So the next problem is something like that. It has 3 parts actually. So this mass is connected to two spring in different configurations. So it's asking what's the time period formula, right, for each of these situations. So first one, let me get started. First one, this mass is connected with 2 springs with 2 different spring constants in parallel, right? And what's the and then if you displace it from the equilibrium position, and if you release, it will go simple harmonic motion, right? And it's asking what's the time period formula in terms of the given variables. So so since they are in parallel, both are connected to the same mass. At any position, the net force would be F1 plus F2, right? And F1 is spring force. Both are spring force for each. So negative K. Let me call delta X. Delta X is the elongation or compression. K1, right? Delta X will be same for both springs because they are connected in parallel, something like that. So no matter how you displace, the displacement will be same, right? The compression or elongation for this both spring will be same. So negative for the second force, K2 delta X, right? Delta X elongation will be same, compression or elongation. So negative K1 plus K2, and delta X is common factor, so that's the net force, right? And then net force from Newton's second law is mass times acceleration, and plus K1 plus K2 times the elongation is 0, right? And so mass acceleration in differential form is just the second order differential equation, and second order derivative with respect to t plus K1 plus K2, right? And delta X or X doesn't really matter, right? So you can just replace delta X with X. So this is again a second order differential equation, right? And if you just compare, so first let's do some rearrangement. So let's divide both sides by mass, right? And this is a second order differential equation, right? And its solution is oscillatory solution. And if you just compare with our standard differential equation, it will be something like that. Omega square x is 0, right? And then your omega, which has to do with the period, right, will be k1 plus k2 over m square root. And then what will be the time period? 2 pi over omega. So 2 pi, it will be flipped km over k1 plus k2. So that's the period formula for the first situation, right? And if the numbers are given, you can right away you can find the time period. So that's how you do. Second is also pretty similar. So if you just say, let's say, displace it before you release, right? If you just displace it by this amount, let's say, right, and then release, it will go oscillations. So if you displace by this amount, let's say x amount, delta x, which is x, let's say, right? So this spring will exert a pushing force, whereas this spring will exert a pulling force. This spring is compressed, right? So it exerts a pushing force on that. So whereas the second spring will actually, since it elongates, it will pull it. So no matter how you displace it before you release, the net force again is F1 plus F2, right? Net force will be same direction, because so in this situation, this will be F1, and this will also pull in that. There will be same direction, not in opposite direction. One will push, one will pull. So, but same direction. So the net, that's a net. So this is again same thing, but delta x is again same. Delta x, which is elongation or compression, can't be different, right? Because they are connected, something like that. So negative k1 delta x is same, negative k2 delta x is same. So you're exactly same. You do the same thing. It just becomes exactly same equation as part A. So is omega will be, you can try exactly same, right? And time period is 2 pi over omega and 2 pi m over k1 plus k2 square root. So exactly same. Okay. And some book says you can just call this as effective spring constant. This k effective is just k1 plus k2. Okay, the last one, part C, was the time period for this configuration. Here two springs are connected in series, right, and finally connected to the mass. So now before you say this is the equilibrium position, so before you release, before you may set into oscillation, you have to displace it a little bit, right, like this, and then release, and then it will go oscillation. So here what's the total displacement? So since they are connected in series, if you displace with right, elongate or compress, what will be the total displacement? Total displacement will be delta x1, which is the elongation for this, plus elongation for 2 seconds. And this, since they are in series, force is same, right? Because they are connected in series, they must exert exactly same spring force on the mass. So, and force, this will be negative force over k1, because spring force is negative kx, right? X is force over k. Okay, negative force is same, k2, right? And then delta x is negative force is common, 1 over k1 plus 1 over k2, right? And then this can be written as parallel combination, right? k1 k2 over k1 plus k2, right? No, times. And then f is negative k1 k2 divided by k1 plus k2 times delta x, right? And now that's it. So that just, now you can just set up a differential equation after that. So f is negative k1 k2 over k1 plus k2, right? And delta x, so this is mass d square x over dt square plus k1 k2 by k1 plus k2. So delta x you can just call x. Divide both sides by mass, right? After that, so d square x over dt square plus k1 k2 k1 plus k2 divided by 1 over mass. X is, so this is again, you can just compare with the standard differential equation, is omega square x is 0. So where omega is k1, you know, k2 by k1 plus k2 m square root, and your time period is 2 pi over omega, so time period is 2 pi, it will flip m k1 plus k2 over k1 k2. So that's the time period formula in this case, right? And you can just call 2 pi m over k, right? You can say k effective. So what is k effective? So effective in this configuration, the effective value of the spring constant is, you know, so k1 k2 over k1 plus k2, okay? Or just leave it like this.